Okay, welcome. We will talk today about about sort of some algebraic, topological, and geometric properties of Fuchsian groups. And the first thing will be to talk to look at the structure of abelian Fuchsian groups. Then look at torsion-free Fuchsian groups, and then look a bit at elliptic fixed points or other fixed points in general. And all of this will allow us to deduce sort of a general theorem, which is that if you have a Fuchsian group gamma and you quotient the upper half plane by this group action, then you can get an induced Riemann surface structure on the quotient, so on the orbit space. Right, so that's the sort of structure of the lecture, and we'll start with the abelian Fuchsian groups. And the first thing you should recall is that if you have two commuting elements in PSL2R, then they have the same fixed points in C bar, and you can also show that they have the same fixed points in U bar, so the closed upper half plane. And of course, if one of the elements is the identity, then they do always commute. So if they're both not the identity, then we get these equivalences. Right, and the other thing to sort of recall before the theorem is to look at discrete subgroups of R with addition, R with multiplication, and S1 with multiplication. And the exercise says that if you have a discrete subgroup of R with addition of these three topological groups, then you then a discrete subgroup is always a cyclic subgroup. So in the first two cases, it's a cyclic infinite, and in the third case, it will be a finite cyclic group. And right, so the first statement is that we want to show the following: that if you have an abelian Fuchsian group, then it automatically has to be a cyclic group. Okay, so if we start with a Fuchsian group, if we start with an abelian discrete subgroup of PSL2R, so it's gamma, then all the non-identity elements have the same set of fixed points by this exercise. And then you can conjugate your subgroup of PSL2R by a general element in PSL2C, such that the image under conjugation is a subgroup of either of these two groups. Right, so we saw that abelian subgroups of PSL2C basically look like elements that are either of this form or this form. And I guess the only thing that's sort of new here is that we can even suppose beta here to be a real number, and that is because we know that gamma preserves the upper half plane, so it preserves some disk in the Riemann sphere, and so the translations will basically, so if you have the upper half plane like this, then in order to preserve that with a Möbius transformation that looks like that, it should be translation in the real direction. So in that direction, in that direction. Yeah, good. Okay, so now we have conjugated gamma in such a way that it lives in either of these two subgroups. And yeah, so here's what I said already. So gamma preserves the upper half plane bijectively, and that means that the image of the upper half plane under this conjugating element nu, this is preserved by this subgroup, and this implies that this new group here cannot have simultaneously elliptic and hyperbolic elements. And so we get that nu gamma and nu inverse is an abelian discrete subgroup. So we know if it's in here or in here, then then it's abelian. And actually, we also want to get more information about the second type. So before this was called G, and now we say actually it's of the following form. So either there's an alpha here, which is a positive real number, so this is just scaling, or this alpha is actually in S1, so it's some sort of rotation. Okay, and then these three subgroups are just isomorphic to these three abelian groups from the previous exercise, and right, and so gamma, nu gamma and nu inverse is cyclic, and therefore gamma is also cyclic because every discrete subgroup of those three groups is cyclic, either infinite cyclic or finite cyclic. In the first two cases, infinite cyclic, and here finite. So much about that. And then there are two exercises here. The first is to exhibit an explicit non-cyclic abelian discrete subgroup of SL2R. So the previous theorem was sort of about discrete subgroups of TSL2R, and this should not work in SL2R. And then the question is, like, if such a thing exists, so something which is non-cyclic, but still abelian in SL2R, then also think about what part of the proof actually breaks down when we try to pick a discrete subgroup of SL2R and try to run the same argument. Okay, so the corollary we get from that, so here the statement is that every abelian Fuchsian group is cyclic, and in particular we don't get two copies of the infinite cyclic group. This cannot be a Fuchsian group. And so when we saw last 2 lectures ago that we can sort of quotient C by Z, Z plus Z, and then we get the torus. 2 torus. This can't happen if we quotient by Fuchsian group somehow. Okay. So now we want to look at torsion-free Fuchsian groups and this notion of strong proper discontinuity. And yeah, torsion-free just means as finite order. So if you so some element gamma gamma is torsion free if it does not exist some n such that gamma nth power of gamma is the identity. They're all different. The powers of this element are all different. And yeah, the group is called torsion-free if it doesn't contain any torsion elements. All the elements are torsion-free. Okay, and now the following are equivalent. So if we have a discrete subgroup of PSL to R, then gamma is torsion-free if and only if gamma does not have elliptic elements. And those two things are equivalent to saying that the action of gamma on the upper half plane is properly discontinuous in the strong sense. So this properly discontinuous was this idea that for any, so if this is the upper half plane, then you have some point, and you can always choose a neighborhood small enough so that when you apply any non-identity element from gamma, it displaces this small neighborhood, so it sends it somewhere else, but far enough that they don't intersect. So those three things are equivalent, and they're also equivalent to saying that the projection to the orbit space is a covering map. Right. So the first thing is to note the equivalence of the first two, which follows from that finite order elements of a Fuchsian group are exactly the elliptic elements. So so the other elements always have infinite order. So parabolic or hyperbolic elements of infinite order and finite order are exactly the elliptic elements. And now, if we know that gamma does not have elliptic elements, then we can take any point in the upper half plane, and since gamma is a Fuchsian group, the orbit of that point is a discrete subset of the upper half plane, and then there exists an open disk in the upper half plane, which is centered at that point with some radius, which we call 2r here, because we will use r later, such that so this open set only intersects the orbit in the single point. So that's the situation. But you have the point, and you have the orbits. So there's somehow sent by gamma around the upper half plane, and then you pick some small open neighborhood of that point, which does not intersect any of the orbits. Okay, so now if we have an element gamma, which has the property that that gamma is W is contained in this intersection. So if we now sort of take half the radius here, and we have our Z naught again. Out here, so we have some Z naught, and then we had a bigger ball B2R, and now we're sort of taking a smaller one, BR. Then and then we assume that something there's some W in this intersection, so it intersects the smaller ball and its translation by gamma. Then we have the following inequalities. So the hyperbolic distance between Z naught and its image under gamma is smaller or equal to the distance from Z naught to W, and then the distance from W to the translation. And so maybe here gamma of Z naught, then somehow here we have gamma BR. So this is the triangle inequality, and but W here is assumed to be the translate of Z, where Z is something in this ball. So there's some Z in here, which gets translated into here. So this is W equals gamma of Z. Somewhere here. So then we get basically 2 times. So this distance, and this is smaller than 2r. And because 2r was chosen in such a way that the only orbits under gamma of Z naught actually is the trivial translate, so only Z naught, and that means that gamma has to be the identity. And so we get this this property that the set gamma such that when we take this open ball around Z naught and translate and intersect it with all its translates under gamma, then that's always empty except for the case when little gamma is the identity. Okay. Right. So this is sort of exactly the definition of this action being properly discontinuous in the strong sense. And yeah, then we want to look at 3 implies 4, and this is basically exactly the sort of the main result for properly discontinuous actions in the strong sense is that this projection to the order space is a covering map. So that's this implication. And then the last implication is to look at 4 implies 2. And right, so if gamma does have an elliptic element, which we call eta, and now we look at a point in the upper half plane, which is a fixed point, then every open disk centered at that point has distinct points that are eta congruent. So this is the group that's generated by eta. So maybe we can draw a picture again. We have Z0 in the upper half plane, and yeah, basically we sort of have some sort of rotations around that point, which are generated by some element eta, and yeah, the statement here is that every open disk which is centered at Z0, so I don't know, maybe open disk like that, or maybe a smaller one, there are some points that are sent to each other by this group, so that distinct points which are eta congruent. And then you're supposed to finish the argument by showing that this actually implies that there cannot exist a neighborhood of this point, the projection of this fixed point in the quotient, which is evenly covered by this projection map. Yeah. Okay, so that's the exercise, also hand-in exercise. Okay, so now we look at elliptic fixed points. And we define it to be some point in the upper half plane, which is fixed by some non-identity element of gamma. And then the result is that if you have a Fuchsian group, then this set of elliptic fixed points cannot accumulate in U. So yeah, the set of elliptic fixed points is discrete subset upper plane. And yeah, to prove that, we assume that they do accumulate, and that means that there's some fixed point in the upper half plane. Maybe, yeah. So this one actually doesn't have to be a fixed point, right? So there's some point in the upper half plane, and a sequence of pairwise distinct elliptic fixed points, such that yeah, they get closer and closer to this point, Z0. And so now we can look at the look at these individual points. So maybe I'll draw a picture again. So somewhere we have z0, which could be anything, any point, and then we have like some sequence of fixed points. So these are all fixed points. And them being fixed points, the stabilizer in gamma of those fixed points is a cyclic group, which is generated by some eta n. And yeah, since they all have distinct fixed points, these elements eta n are also pairwise distinct. Okay, and now we use the fact that gamma is a Fuchsian group. So for Z0, there exists some epsilon such that if we take the epsilon ball around Z0 and look at its translates under gamma, then it only intersects finitely many of its translates. So this set here is finite. So that's, on the one hand, we have sort of this property, and on the other hand, for the same epsilon, there's some number such that sort of all of the points in this family of fixed points, which are bigger than some n epsilon, they all lie in this ball here. So that's what it says here. For the same epsilon, there exists some n epsilon such that all n bigger than this n epsilon, those fixed points end up in the small epsilon ball around Z0. Right, and then the problem is that that we have these eta n's which generate the stabilizer of the individual fixed points here, and we said they're all pairwise distinct, but now actually they are all fixing those fixed points, but they all lie in the small neighborhood. And so now we actually get infinitely many distinct elements, which lie sort of where this intersection is non-zero. And so that gives a contradiction. Okay, so now we know that the set of fixed points is discrete. Okay.
Yeah.
Good. And now we have this corollary, which uses sort of a similar argument as before. So now, if we take a Fuchsian group, then there exists some open hyperbolic disk of positive hyperbolic radius, such that the set of elements in gamma for which this intersection here is non-empty. This is exactly the stabilizer group. And what's more is that actually this element gamma here preserves this hyperbolic disk. So basically we have our fixed point Z0. We can choose a hyperbolic disk around it, such that the translates which this intersects are exactly those which actually fix this point Z0. So that's the stabilizer of Z0. And how does the stabilizer act? It acts by an automorphism of this hyperbolic disk. Okay, so now we start with some open set, some point in the upper half plane, and since gamma is a Fuchsian group, the orbit is discrete. So so we get this property that there's some hyperbolic open disk which intersects the orbit exactly in that point. And we can also assume that that this is the that there are no fixed points of gamma, because the fixed points are discrete. So we can always pick sort of 2r small enough so that if there are any fixed points in this open ball, then the fixed point could be Z0, and if the Z0 is not a fixed point, then there are no other fixed points in that disk. Right, so since the non-identity elements of the stabilizer are elliptic, and they fix Z0. We have the following. So the elements in the stabilizer, they actually already fix this hyperbolic disk. Okay, right. So it fixes this hyperbolic disk because eta acts as an isometry, and in particular we get that this set here, which is the set of all elements in gamma which have this property, that definitely contains the stabilizer. And then it's sort of exactly the same trick as before. We look at we suppose there exists some element W in this intersection. And then, the triangle inequality gives us that this distance here has to be smaller than 2r, but under the points which are smaller than 2r, there are no translates of Z0. So then gamma of Z0 has to be Z0 itself. and that means that gamma is in the stabilizer already. So then you get not only the inclusion of the stabilizer, but actually equality. And that's that's what we wanted to show here. Right. And this the second statement was sort of shown at this part of the proof. Good. Okay. So now we look at the Fuchsian group and again some point in the upper half plane, and we can call this type of disk a pre-covering disk. So it's not quite a covering disk because it's not a covering map, which is this part of the Hendon exercise. So, but it's something analogous. So we call it a pre-covering disk. Right, and so now we look at the following corollary. So if you have a Fuchsian group and you take out its set of fixed points, so the elliptic fixed points are those that lie in the strict upper half plane. So gamma could have fixed points which lie in the closed upper half plane, but those that lie inside are exactly the elliptic fixed points. And if you take them out, then then the first thing that one notices is that the complement is stable under gamma, and the action on the complement of those elliptic fixed points is actually properly discontinuous in the strong sense. Right, and then we get that the projection from that complement to the orbit space, that is a covering map. So somehow if you have some elliptic fixed point for some torsion elements of gamma, then they do something like that around that point, and so that means basically that central point, that fixed point, is exactly what messes up the proper discontinuity in the strong sense, and so it will still be properly discontinuous in the weak sense. But if you want something in the strong sense, you have to take those points out. Right. Yeah. So it's a bit like if you are sort of in R2 and you look at like rotation around 0, for example, then the quotient space should be something like a cone, right? And then here you have some singularity. And if you take out that point, then you have a covering map. But if you leave it in, then you don't. Okay, so what's the proof? What's written here is right, that you can just take the open disk from the previous statement, this one here, and this is a pre-covering disk around a fixed point. But if it's not a fixed point, then this gives you a covering map. Right. Okay. Any questions so far? Okay. so that was that. Okay, and now we look at the next result, which says that if you have a Fuchsian group, then if gamma contains at least one elliptic element and one non-elliptic element, then the set of elliptic fixed points has at least one accumulation point on the closure of U, so U bar, and yeah, so the accumulation point we know does not lie within U because the set of elliptic fixed points is discrete in U, but it could have an accumulation point which lies sort of on the boundary of U, and the boundary is R bar, so it's R plus the point at infinity. And yeah, if you look at that in the disk model, then this would be the upper half plane, and then R is sort of this part here, and then there's some point infinity, and so then you get a circle at infinity. Okay, so to prove that, we start with an elliptic element, eta, and some non-elliptic element, gamma. And now if we take a fixed point of eta, then we can look at the following expression. So we conjugate eta with gamma n times, and yeah, and what do we get if we apply that to gamma to the n z naught? Is that here gamma to the minus n, gamma to the n, they cancel to give the identity. Then z naught is a fixed point for eta, and we just get gamma to the n z naught. So this this lies in U still, and yeah, and now we can look at the set of all of those translates of z naught under these this non-elliptic element gamma. So all of these are fixed points, and since gamma is not elliptic, we have that all of these points are actually pairwise distinct. And right, and so now we have an infinite set of a compact set, because if we take the closure of U, then this is homeomorphic to the closed disk, which is compact. And infinite set subset of a compact set always has an accumulation point. And yeah, we already showed that the accumulation point cannot lie inside the upper half plane, but has to lie somewhere in the boundary, and that is R bar. Okay. Good. So now we already know a few things about fixed points and stabilizers. And now we want to show that the stabilizers are always cyclic groups. And right, so we've already talked about elliptic fixed points, which are those that lie strictly inside the upper half plane. And now we can also look at parabolic or hyperbolic fixed points. And so yeah, we call a point in U bar parabolic, a parabolic fixed point if it's fixed by a parabolic element of gamma, and a hyperbolic fixed point if it's fixed by a hyperbolic element of gamma. And yeah, that's the observation. What I just said is that the parabolic and hyperbolic fixed points, they have to lie on the boundary, so on R bar. Okay, so now here we also introduce this notation. Pi is just a projection from SL to R to PSL to R. And now we have two lemmas. One lemma about parabolic fixed points, and on the next slide, essentially the same lemma, but for hyperbolic fixed points. And for both of those, we want to show that gamma of Z0 is so the stabilizer is cyclic. Okay, so we start with the parabolic fixed point, and by definition that means there's some parabolic element in gamma which fixes this fixed point in R bar. And yeah, without loss of generality, we can assume that Z0 is actually infinity. And yeah, just can think about why. And now, yeah, under that assumption, we know that this parabolic element that fixes Z0 is actually of this form. So it's 1 beta 0 1, where beta is a real number. And yeah, so nu is that the Möbius transformation associated to that matrix. And right, and now if we take any element in the stabilizer, right, so we already know that all the elements which are of this form, they fix Z0, so they fix infinity, and they all commute. But now the question is, are there maybe some other elements in the stabilizer which still fix infinity? So they sort of come from matrices of this form. So A, B, 0, A inverse. So the 0 was that infinity is a fixed point. So now if we take some element sigma, which does lie in the stabilizer and comes from a matrix of this form, then yeah, if sigma is a hyperbolic element, we can assume without loss of generality that actually B is 0. And yeah, this is again sort of exercise to think why exactly that should be true. And now we can conjugate our initial parabolic element 1 beta 0 1 by this sigma in this simplified form. And what we get is just through matrix multiplication, we get a matrix that looks like 1 a squared beta 0, 1. And if you repeat that conjugation with B, then you get elements that are of this form, and they have some sort of A, the power of A with beta in the upper right corner. And now if we take n to infinity, that means that these matrices get closer and closer to the identity. And but now all of them sort of give rise to elements in gamma, and if they get arbitrarily close to the identity, that implies that gamma is not, or the pre-image of gamma under this projection from SL to R is not discrete, and that gives a contradiction, and so actually sigma cannot be hyperbolic. And if sigma is actually parabolic, that means all the elements which do fix Z0 are parabolic, and there we know parabolic elements commute with each other. And so we know that the stabilizer is abelian, and discrete abelian subgroup of Fuchsian group is cyclic. That was the first part of the lecture. Good. And now a similar argument for hyperbolic fixed points. So again, Fuchsian group, gamma, some hyperbolic fixed point, which again has to lie in R bar and cannot lie inside U, but just on the boundary. And again, we want to show that the stabilizer is a cyclic group. And and so we have a hyperbolic fixed point, then we have by definition an element which is hyperbolic in gamma, which fixes that point. So now mu is a hyperbolic element, and we can assume again without loss of generality that the fixed points of nu are 0 and infinity. And and then we just take Z0 to be infinity, and that means we have a simplified presentation of our element nu as the Möbius transformation associated to element of a matrix of this form, alpha 0, 0, alpha inverse. The idea is, of course, you sort of have the upper half plane, and then the hyperbolic elements sort of either scale everything in this direction. So make everything bigger or everything smaller, and fixes 0 and infinity. And now, as before in the previous lemma, we take some other element which lies in the stabilizer of Z0, and has the following form. So now we know by the previous lemma that that this element cannot be parabolic. So A cannot be equal to plus or minus 1, because the stabilizer we saw could not, if it has some parabolic elements, then it cannot also contain hyperbolic elements. And since we have some hyperbolic element here, we cannot have parabolic element in the stabilizer. And yeah, so now that sort of implies that A cannot be equal to plus or minus 1. But now if we take, now if we try to see what happens when B is not equal to 0, then we can do a similar computation as before. So we conjugate this matrix by alpha 0, 0, alpha inverse, and get again an element that looks like this. So here we have alpha squared beta now, and alpha we know is not 1, and so we get again some sort of family of matrices which if they're part of gamma, then gamma cannot be discrete because the pre-image under the projection to PSL to R is not discrete. And so that happens when B is not equal to 0. So we conclude that B has to be 0. But now if we have things which are of this diagonal form in SL2R, then they commute, and they have the same fixed points, namely exactly 0 and infinity, and then the stabilizer is again abelian, and being discrete, we can again conclude that the stabilizer is cyclic. Good. Okay. Okay. So now we've proved the theorem, which says that if you have a Fuchsian group, then if you look at all the fixed points in U bar, the stabilizer is actually a cyclic group. Okay, and then then with these results, you can prove sort of this theorem, which we will not give the full proof. And the theorem says that given any Fuchsian group, the orbit space admits a Riemann surface structure, which makes that projection from U to U modulo gamma a holomorphic map. So that's what we saw for the torus. If you have C and then you quotient out by this lattice or maybe by some other lattice. So this is Z squared embedded into it's actually Z plus Z I. Right? If you take this quotient, then this is isomorphic to the 2 torus, and then you can get a Riemann surface structure basically because you know that in the 2 torus, like any point around some any open neighborhood around some point corresponds to some open neighborhood here, and all the pre-images are sort of scattered in a nice way around C, and you can take the complex structure on all of those small things and project it down, and this is gives a well-defined Riemann surface structure. And exactly the same thing works for Fuchsian groups. The only problem is that you might have some torsion in the Fuchsian group, and that gives sort of singular points. And in order to describe that very precisely, you need a bit more work, and that's why the proof is sort of not part of these lectures.